Everyone, this is Samundra Adhikari. This summer, my colleague Aisha and I had an incredible opportunity working on a project that aims to address a very critical social issue in Cape Town. We were Project 25 of Data Plus, and our title of the project was Energy Transition During Energy Crisis, Cape Town's Experience. Just to give you a brief overview of what our project is, we need to understand about South Africa. South Africa is the 14th largest coal emitter in the world, which means the electricity production is heavily dependent on coal. But coal, as we know, is very restrictive in terms of availability in nature. So sometimes electricity produced is less than the electricity demanded. Uh, so this leads to frequent blackouts in various communities and affecting personal life, economic activities, and everything. To mitigate these problems, wealthier neighborhood have installed solar panels on their rooftop. So whenever there is power blackout, they can generate their own power. However, poorer households cannot afford the installation, and that creates something called energy appetite. So given this, our research goal is to suggest policy goals or incentives to encourage the utility to employ a more equitable load setting schedule. We are doing this by basically just identifying where the solar panels are. We aim to study the patterns, any kind of pattern involved in how the solar panels are installed or what kind of community the solar panels are. So, talking about our data set, our data primarily comes from satellite imagery of Cape Town from year 2000 to 2023. The images are in ECW format. In addition to that, we also have their corresponding tiles in GeoTIFF format, and the pixel resolution is 1025 per 1025. The area of our study is 2500 kilometer, and the size of these images are more than 100 GB. We also have various kind of CSV files. It's worth 30 GB of data, uh, and these files they contain electricity transaction data. So workflow. Our research started off with us manually annotating our solar panels. We also are training our machine learning model side by side, so it can do the rest of annotations for us. We are doing this because we want to find installation year of solar home systems by comparing the annotations from different year. Installation year will also allow us to identify trends of solar house installation. It will also allow us to test realistic scenarios in our energy model and also compare the previous load setting schedules with what an optimal schedule would have looked like. Then we will also determine the capacity of the solar panels and PV arrays and further continue our annotations using learning model, machine learning model, and ultimately suggest policy goals for equitable load setting policy. Now, let's talk about a very crucial part of our research, solar power annotation. First, we experimented with various data types from Massachusetts, from Valencia, and a couple of just random images we found on Google. We experimented with various annotation tools such as QGIS and ArcGIS. Uh, while we started doing our annotations, we started observing that wealthier households can be identified from the solar imagery with outdoor amenities and high quality roofing materials. These kind of households have more solar panel installed in comparison to poorer ones. And we also found that higher concentration of rooftop solar panels are found in public spaces such as shopping centers, hospitals, and these spaces are generally located near neighborhoods and communities that have a few to no solar panels. Uh, in our studies, this means poorer communities. Uh, we also faced issues due to the resolution of the images and visual observation, as some solar arrays are not easily detectable, especially on darker rooftops. However, we plan to do further annotations by using our machine learning model Solar Mapper, which is a state of the deep art convolutional neural network. We trained this network using the Massachusetts Rhodes dataset, and we plan to train it further on the Cape Town dataset to recognize more solar arrays in overhead imagery. The deployment of this model on our dataset is planned for the next steps. Uh, and this is a visual representation of what the wealthy household looks like, uh, and an overview of what poorer household with respect to our study looks like.
As mentioned previously, in addition to the satellite imagery, we were also given a number of CSV files containing transaction details of electricity services in Cape Town. We received these datasets toward the end of the program. However, we were able to analyze them and extract useful insights from them. Some of the most important variables in these datasets include service contract numbers that were encrypted to preserve privacy of their owners, location of the electricity meters as geometric coordinates, location and time of each electricity blackout, and the transaction data of each of the services. After extensive cleaning of these datasets, we merged some of them by spatial joins and others by common column entries. We then selected the important variables that we needed and created a final dataset that includes the hashed contract account number, the load trading block in which these contracts are effective, the purchase start and end date of the service, and the units purchased. Next, we were interested in estimating the capacity of solar panels to give us insights into the energy generation in the region. Unfortunately, we don't have any data about solar panel installations or any of their characteristics. The only information we have about them is their area, which we can calculate from their annotations on the overhead imagery. There are some research papers that discuss methods to estimate the capacity of solar panels based only on their area. They concluded that there is a really linear correlation between the two variables. So to calculate the capacity, we used their derived linear equation, which is as follows. The capacity I of solar panel is equal to gamma, a proportionality constant, times alpha, the area of the solar panel I, plus eta, the error of the prediction. Gamma is uh, estimated to be equal to 1 kilowatt per installation that on average covers an area of about 6.5 meters squares in the region of Cape Town. This project is very interesting. Unfortunately, we didn't have enough time to finish all the work that was planned. So in the future, we hope to continue the annotations on imagery from different years. We can use the a machine learning model that we talked about previously to automatically detect the location of new satellite of new solar panel installations. In addition to that, we can identify the installation year of new solar panels. All of this information can help us suggest a more equitable load shedding schedule. So that's it for our presentation. If you have any further questions, please don't hesitate to reach out to us via email. Thank you.